So let us now study about the polybasic acids. So you have studied this already. How do we define a monobasic acid? Or we even say it is acid whose basicity is 1 is nothing but a monobasic acid. If it can give 1 H plus ion per molecule. For example, if we're talking about HCl, it's a monobasic acid because when it dissociates for one molecule getting 1 H plus ions. Okay, so dibasic acid is the one wherein you are getting 2 H plus ions per molecule. So H2SO4. Okay, now even acetic acid can be a good example because it dissociates into CH3, CO, acetate ion and H plus ion. So don't just go by the number of hydrogens. How much H plus is dissociated per molecule of the acid is what determines its basicity. Alright, so in this case for one molecule you're getting 2 H plus ions. In general we call it as a polybasic acid or uh, polyprotic, yes, polyprotic acid if there are more H plus ions per molecule. Okay, 1 and 2 we call di, mono, di and tri, and after that it is polybasic acid or a polyprotic acid. That means there are more than 2 H plus ions per molecule. Alright. Now oxalic acid also here is example for a dibasic acid. Similarly, we have polyacidic base, but it is not in the curriculum. But what is polyacidic base? A base whose acidity is 1. And for base we say if it is 1 OH minus ion, we say a monoacidic base, 2 H plus ion, diacidic base, and otherwise if it's more, polyacidic base. Alright, so example for tri or this will also be phosphoric acid, 3H plus per molecule. Alright, so in general let us understand this. Let us say you have a dibasic acid because it has 2 hydrogen, it dissociates. This is a dibasic acid. What happens the moment you put it in water, or how does it dissociate? You are going to get I'll just write H plus for now, it's hydronium anyways. So H plus, first step it is H plus plus, what are you going to get here? HX minus. So in one step it is not happening, then the H plus minus ions that dissociates in the presence of water. Even if I don't write, it is implicit to give you H plus again and X minus. Okay, so this is an acid. Okay, when it changes into this one proton it loses, this is its conjugate base. Here also this is acid and this will be the conjugate base. Here the first proton is lost, here the second proton is lost proton. Okay, it is a dibasic acid, that means two protons or 2 H plus ions will be lost. But how does it happen? Proton, hydrogen ions are the same because H plus is nothing but a proton. So I can interchangeably use these words. So in the first step, one proton is lost and you are getting a conjugate base which acts like an acid in the second reaction. And you are going to get the conjugate base again. So now I have two acids. Out of them, this is going to be the stronger acid. So I will say H2X is stronger than HX minus. Okay, this is a stronger acid because you know the tendency to give proton is stronger here because it only has to lose one proton. But once it is converted into Y, I will tell you why is this stronger, because here, because it is difficult to remove H plus from negative charge, the ion. What is the meaning of that? You already have a negative charge here. That means the nucleus, there are more electrons, correct? So it is difficult to remove H plus because it's already having a negative charge. I still want to take from H plus. It is already having an imbalance. I don't want to do that. It is not allowing me to do that. That's the reason it is not easily giving you H plus. So that's why this is going to be a stronger acid. So if you write this Ka here, if I write K, this is as Ka1 and Ka2. What is Ka here? This into this divided by this into this divided by this. We know that. Ka of a stronger acid will always be greater, okay, the initial acid, and as and when it goes on dissociating, the successive acids which are formed are weaker. Okay, the reason I told you, it is difficult to remove proton from a negative ion. Alright, so therefore when you have reactions like this is always considered to be the primary reaction. Remember, I told you, when you have a series of reactions which are happening, the one with the greater Ka or the equilibrium value, that is the one which is considered as the primary reaction, and that is the one wherein I have to write all those table, initial, extent, equilibrium and all that. Okay, so in general, when you're having a just to summarize, polybasic acid whose basicity is more than 1, which in other words means per molecule it gives me more hydrogen ion concentration. And if I removal of hydrogen ions happen in steps. The first step is always, whatever is there in the first step, that is always going to be the stronger acid, and it has a greater Ka value, and that should be the primary reaction. Alright, so now also let us consider factors affecting the strength of an acid. Very important, this is a very important topic, they can ask you questions. Factors affecting acid strength. How do you decide which acid is stronger, which acid is weaker? You know there are some acids which are stronger, some are weaker, but what is the deciding factor? Okay, now the deciding factor is the extent of dissociation. How easily it can dissociate to give you H plus ions, more easily it can dissociate. Okay, easily gives H plus ions. If there is an acid which is very easily it is losing H plus or giving a proton, then it means it's a stronger acid. The easy it is stronger. And what are the two factors? It depends on the strength and polarity. Let us see how these two things are related. Okay, lower the strength, lower the strength, it is, now strength, I mean it's the force of attraction between the molecules. Okay, lower the strength, easy to break or easy to dissociate. Lower the strength, easy to dissociate, therefore it is going to be a stronger acid. Okay, when it is easier to break the bond or dissociate, if the force of attraction is not that much, it's easy to break them, and stronger is going to be the acid. And in terms of polarity, greater the polarity, or when I mean polarity, it is electronegative difference. If there is a greater difference, that means charge separation is greater. Charge separation is greater, then it is easier to dissociate. Again, it is going to be a strong. So when can the acid be strong? If the force of attraction is very weak, it is easier to break them because there is weak force of attraction. They are not strongly held, they are loosely held. You can break them easily and you can separate the H plus ions. So the lower the strength, lesser the force, easy to break, stronger is the acid. In terms of polarity, if the electronegativity difference is greater, let us say this is H and this is fluorine for example, high electronegativity difference. So there is charge separation which is greater, the electrons are almost closer towards the fluorine, correct? So it's easy to break hydrogen because the separation is greater. Imagine an HF, okay, the electron shared pair is almost near fluorine. I can very easily remove the hydrogen because fluorine likes it. Okay, so greater the polarity or greater the electronegativity difference, or in other words, if the charge separation is more, I am talking about charge separation, the electron is more farther from the H plus ions, easier it is to break them and stronger will be the acid. So if you understand these two things, you can very easily arrange everything in the ascending, descending, and answer questions like which is stronger, which is weaker. Alright, so let us now talk along a group. If you go down along a group, like for example, you have H plus, HCl, HBr and HI. Okay, so it is if you are talking the increasing order, this is the increasing order. HI is stronger in comparison with HBr, HCl, and at last it is HF. Okay, so if you go down the group, it is acid is becoming stronger, or the strength increases down the group. And the reason, what happens if you go down the group, here hydrogen is same but chlorine is large, bromine is still more large, iodine is still more large. Hydrogen size is same. The force of attraction is greater here, force of attraction is least, because you have nucleus here and nucleus here. The separation is greater here. So the force of attraction is greater, that means easy to separate, therefore it is going to be a strong acid. Okay, so down the group the acid is going to be more and more stronger. Let us now talk about what happens across a period. Okay, so across a period, this is my across a period. Here we do not talk in terms of strength or force of attraction. Here we talk about polarity. Okay, like for example, let us say what are the elements? Carbon, nitrogen, oxygen and fluorine, which are in the same period. So if you take a compound like methane, ammonia, water and fluorine for example. Okay. Okay, so now HF is, so what happens if you are going across the period? Across the period also acid strength increases. Why? Because here almost no charge here, it's a non-polar molecule. There is a large charge, I told you this. It's almost near the fluorine. So very easily, this is a greater polar molecule, greater negativity difference, separation of charge is greater, easy to break, therefore it's a stronger acid. So for the same group, if you're going down here, this is the weakest acid down the group. This is the strongest acid across the period. So down the group you go or across the period you go, the acidic strength increases. Alright, so now let us understand common ion effect. Now this is a very general thing, okay? If you understand this logic, it's easier to solve the numericals, alright? So what is common ion? The effect on equilibrium, I can even write like this, common ion effect on equilibrium. Effect on equilibrium when a common ion is added to the reaction mixture. Alright, so let us take an acid, acetic acid, which is a very weak acid. Okay, aqueous. Let us say it is giving you acetate ion plus H plus ion. On dissociation, it's giving you H plus and acetate ion. Okay, now what is going to happen here is, these are the ions. Now let us say equilibrium has established and these are the ions in these. There are few ions and there are few acetic acid as it is, because it's a weak acid. Now when I say common ion, what is common? If anything which is if you add any ion which is already present in the reaction mixture, the added ion should be common in the reaction mixture. Okay, so in general, let me say, if I write like this, what is Ka? Ka is acetate ion into H plus, because it's an acid, divided by CH3COOH. Okay, now there are two ways to understand this. If I add, let us say if I add H plus ions, I'm adding more. After equilibrium is established, I'm adding more of H plus ions. According to Le Chatelet's principle, if H plus is more, it should reduce it so that equilibrium is re-established. So if I have to reduce this, because I've added it, it will react with this, okay? So it will try to decrease it, and when it reacts with this, CH3COO minus concentration also decreases, because this is reacting. So I'm adding this, it tries to reduce this by reacting it with this. This is also reducing and you are getting more of the product. This becomes more. Okay, I repeat, if you are adding this, according to Le Chatelet's principle, it tries to reduce it, and when it tries to reduce it, it tries to react with acetic acid, acetate ions, and the reaction is proceeded in the backward direction. So if you are adding any of the ions, the reaction proceeds in the backward direction. That means more of acetic acid you're getting back. Alright, or here also you can see, if this increases, that means Ka increases. If the equilibrium constant increases, it means that the reaction is proceeding in the backward direction. Alright, so what happens? How do I summarize this? So what is the effect, common ion effect? Common ion effect just tells that there is a shift in equilibrium on adding a substance that is providing more of the ions which are already present, and the shift is always in the backward direction. Okay, so that's about common ion effect. In the next video, I'll be doing the hydrolysis and buffer solutions.